What's up? Awesome. Morning. Afternoon, I guess, not morning. Man. All right, so it's 12:30. Packed house today, for sure. Let's get started. Lord, thank you for bringing us together this afternoon. Pray that you would continue to help us get through this semester, help us to stay strong, to stay motivated, and to excel. In your name we pray. Amen. All right. Wow. All right, so today we are going to continue with what we did last time. Let's recap a little bit. Afternoon. We'll start our recap, right? So the big question last time was instantaneous centers. Right? So last class we started talking about rigid body kinematics, right? And specifically, we addressed if we have something moving in general plane motion, right? It's a combination of translation and rotation. So we're going to say that it's translating by a certain known velocity. And then we're going to hold that point fixed, and then we're going to rotate about that point, and we can figure out how we can track any point on our rigid body by doing this, right? Remember the idea of this wheel, right? The idea of a wheel. I'll draw this up on the whiteboard here. The final wheel that's rolling on the ground, right? This is a wheel and it's starting point. We can track this point A around the edge, right? At some final point, this will have rotated and translated down the road, right? And let's say A is here now, right? But how did we get there? We can model this motion, right? If this is the center of the wheel, we can model this motion as, what if I just pick this wheel up, move it here, and plop it down, right? Then A, if B at this point, we'll call it A prime, right? Then I can rotate this around O until I get to this displacement, right? So I travel through that theta, which would cause some rotational velocity, right? Now the rotational velocity is what? Well, it's going to be the tangential velocity, right, is equal to omega across r, right? So it's the velocity divided by the radius that we are away. Right, so then there's this idea of the instantaneous center. It only applies for velocities, right? And this is the idea that there is some point in space that if I were to stand on that point in space, it would look like my rigid body is rotating around. Right? There would be no translational velocity. It would just look like a pure rotation about that point in space. And that point in space can move, but at every instant, right, every freeze frame that we take of our motion, there will be one. And how do we define it? Well, you take the velocity vector of each point on your body and you draw the perpendicular to it, right? So you draw a line that's perpendicular to each of those, and where those two lines cross, that's your instantaneous center. Right? We did a problem where if you missed that one, go back, watch last week, Thursday's lecture, and we have two methods of doing this, right? We have the overall method of doing this, which is treating everything as a translation by some known value and then a rotation about a fixed point. Or we can do instantaneous centers. Now, instantaneous centers don't always work. They only work for velocities. You can't use them for acceleration, right? But they are helpful in simplifying some of our problems. All right. We're going to continue with this stuff today, right? As a means of recapping, right? After we talked about velocity, we said, well, we can do the same thing for acceleration, right? So we solved this problem twice last class. We did it once using the rigid body method, and we did it once with instantaneous centers to find the velocities. Now we're going to do it again, and we're going to try to find the accelerations of this link BD. That's the acceleration of the connecting rod and the acceleration of point D. Or, since that's a point on the piston, the acceleration of the piston. Okay. Excuse me. Excuse me. Woo. It's dusty in this mask. It's dusty. All right. So what do we know? Right. I've got this crank AB. It has a constant angular velocity of 2,000 RPM. Right. And I want to find for this position, right? So we know something about the geometry of it. And then we want to find the acceleration of the rod and the acceleration of point D. All right, so how do we do it? Good question. How do we do it? First, we need to start with what? Well, remember, a lot of these problems end up boiling down to our relative equations, right? A relative acceleration equation. But the principle of it is this, right? Well, first off, we have that crank arm, right? And that crank arm is what? Well, it's got a constant velocity, right? So we have to figure out what the acceleration of this crank arm is going to be from A to B. And so AB, right, we know this is 3 inches. It's at an angle of 40 degrees with the horizontal, right? And because we know that omega is constant, we know that alpha is going to be 0, right? this will not be accelerating angularly. However, remember, when we talk about the acceleration of point B, we're talking about it in terms of normal and tangential components. So there's no tangential acceleration, but there is an acceleration pointing back down towards B, the normal component of the acceleration, right? So we can figure out what this is. The normal component of the acceleration is due to the angular velocity. And where did that come from? Well, we defined that a while ago, right? When we were talking about kinematics for points, right? For particles. When we talked about normal and tangential accelerations or normal and tangential coordinates. We can plug in some numbers, right? So I'll get 3/12 times 209.4. What didn't I show you guys here? The conversion from RPM to feet per second, right? Which one? The conversion? Yeah, AB is R omega squared AB. That's given. That comes from that derivation where we had R cross omega from a couple of weeks ago. So this will give me an acceleration. Oops, sorry, can't read my own writing. 10,962 feet per second squared. Right? We can break this down into X and Y components. Right? So you're looking here, right? I can have ABY and ABX. Right? So I can break this down into X and Y components. And we're going to do that. Why would you want to do that? Well, everything's going to be measured from this XY coordinate system, right? So I need to know what portion is in the X direction and what portion is in the Y direction, right? It's important for us to know this. So if I write this as a vector, this is the magnitude of my vector times the cosine minus the sine of 40 in the j. So all I'm saying here, all this is saying is that the x direction component, the I component, is negative, and it's getting scaled by cosine 40. Right? So it's moving to the left, it's pointed to the left, and we've got cosine of 40 degrees. That's the leg of the triangle, right? In the I direction and in the j direction, right? So let me get my coordinates up here. Y, X, right? Remember, X is I, Y is J. So we can do the arithmetic here. And that's perfect. So that gives us, all right, so that gives us what? Well, that's our acceleration for B. Why is that important? Because remember, we're going to draw this out, right? So that is a pure rotation. That crankshaft is purely rotating around point A. The next part is to figure out the acceleration of the length BD, right? Well, if I draw that, well, this is B and this is D, I know the acceleration of BD, right? Or of B, of point B. Here it is. This is my normal acceleration of point B, right? At this instant, point B is accelerating by the amount we just found up there. So we know what that is, right? I can just drop this and call this AB, right? Some vector AB. I also know that point AD or point D has to have an acceleration that's in either of these directions, right? Why? This piston is in the housing. It is forced to move horizontally. It cannot move out of the housing. Otherwise, we have big problems, right? So it's going to stay in there. It's going to move left to right. But the problem is, I don't know from the information that I've been given whether it's moving or it's accelerating to the left or it's accelerating to the right, right? I don't know that. It can do either. There exists a condition if you run this either way in which that would happen, right? So we're just going to have to pick one and roll with it in a second, okay? We'll talk about that in another second, okay? We know that this angle in here is 13.95 degrees. How do we know that? Well, we came up with it last class. Remember? Check the problem. This is, remember, this is the same, this is the follow-on to the problem that we used for most of last class to run these examples. So that's the final state. How did we get to that? Well, we can treat link BD as every point being accelerated by this vector, right? Remember, I'm going to keep, and if this is my center of gravity, right? Every point on this rigid body, we're going to say this is all being translated by this acceleration. You know, we're all moving at that, and then we're going to add our next point where I keep B fixed, and this is going to create some omega BD and some alpha BD, right, about that point. So that point's fixed, which means that we now have some acceleration, right? And I'm going to draw it with 3. So I know this one has to be the normal, right? The normal has to be pointed back towards the radius of curvature. But again, I don't know which one of these tangentials I'm going to be using. How are we going to pick? We're going to pick one, right? We're going to pick one, and we're just going to do the problem consistently, and then our numbers will tell us, right? If we get a negative, that means that we chose the wrong direction. Right? So it's not, there's no right or wrong one to pick. Pick whichever one you think makes the most sense. But remember that you do have to be consistent, right? Because it's going to matter. If you're not consistent with it, then your math, your sign errors are going to cause you to get the wrong answer. Okay. Everybody okay with this so far? We follow, we tracking. Is there any questions so far? No? Good. So that 13.95 came from the original problem. You know, we did a bunch, remember we did a bunch of trigging there. What we ended up doing is, so I'll say this. We know that this bar is at 40 degrees, right? This here is 40 degrees, which means that this angle in here, well, that's the not the that's at 40 degrees. And when we found that's 40 degrees. When we found the velocity, we had some angle, right? We had some angle for our velocity, right? It was at some offshoot. It's actually not showing. So you have to kind of go back to the velocity. No, thank you. Let me draw it better so that we can actually see it. So when we drew our velocity here, right, it's this green arrow that's up there, right? The velocity is tangential to that point, the velocity of B. The velocity of B is at 90 degrees to my crankshaft, right? So if we drew this, right, it would be somewhere like that, yeah. So we know that between here and the horizontal has to be 50 degrees. Why? Because I know that between here and here is 40. Right? I know the angle from the horizontal up to there, right? So if that's 50, then we can figure out what this, we can figure out this angle in here, right? By, or this angle here, which we call beta, by doing law of sines, right? So, okay, I did that completely, I explained that horribly. Let me try it. Let's try it one more time. Let's try it one more time. This is my complete system, right? Why don't I just go back to the actual picture? This is my triangle right here, right? I want to know this angle. I know this angle and these opposite lengths. Sine of 40 degrees over 8 inches is equal to the sine of beta over 3 inches. We just used law of sines. That's where it came from. Apologize for being convoluted about it. Okay, so here we are, where we got this going. I'm not going to make any decisions yet, but I'm going to write some things down. Because what do I know? Well, I know that the vector for my acceleration has to be horizontal, right? This has to be plus or minus the magnitude of my vector in the I direction. It has to be, right? It has to be constrained along that horizontal path. It can't go up and down. It's in the housing, right? And this is going to oscillate because of my rotation, right? Because think about in an engine how your pistons work, right? They go up and down and up and down and up and down. Well, that's what they're designed to do. I can also define A of D with respect to B in the normal direction, and I'm going to write this as the magnitude. Right? So I'm not picking a direction yet, I'm just writing the sheer amount of it. And what is this? Right, well, that's B, that's BD, right? BD is the length of BD, right? The length of the bar, which is 8 inches, times omega BD squared. And what is that? Well, we got that in the previous problem, and that's 62. That's going to be 62. So this is going to be 8 over 12 times 62 squared. Which gives us the acceleration of point D with respect to point B in the normal direction, which is nice because that's an easy win for us, right? We know that that has to be pointed back along my bar. If we wanted the actual vector, right, that's going to be the magnitude of AD B normal times negative cosine 13.95 I plus sine of 13.95 G. Okay, So let's go back here. We're talking about these green accelerations, right? Specifically, we're talking about the normal. Right? We're talking about the normal here. If I'm talking about the normal, the angle here is this 13.95. All I'm doing is putting this vector into x and y components, right? Into I and j. That's all I'm doing. So the cosine, right? And what do the components here look like? Well, they'd have to be to the left and up, right? To the left and up. That's why we have negative and positive there. Okay. So great, we can do that, and we can get this out to be, we did the math. In feet per second squared. And we can do something very similar for the tangential component, right? We can do something similar for the tangential component. So we're going to look at the magnitude first. Right? That's what the absolute value signs around it mean. It means it's the magnitude, it's the amount. Right? And the magnitude in the tangential direction is just the length of BD times the angular acceleration of BD. We don't know the angular acceleration of BD yet, right? That's one of the things we're trying to find. But if we put this in as 8 over 12 times alpha BD, we can write that as 0.667 alpha BD. Or 2/3. And 12 is 2/3. We can do the same thing, right, if we want to talk about this as a vector, which we will. And now is when we're going to have to pick. Now, well, we don't have to pick yet, but we're going to have to pick soon. So if this, I want this triangle, right? I want to know what that is. Well, if this is 13.95 in here, right? This is 13.95 in here. Isn't it also the same angle as in here? That's also 13.95. So if that's the case, right? And notice I'm going to write this as in terms of plus and minus still. Well, I guess that's not changing. This is going to be BD times alpha BD. This is going to be the magnitude of ADB tangential times plus or minus sine of 13.95i plus or minus cosine 13.95 in the show. So we can come up with an expression for this, and we're going to leave it in terms of the sines and the cosines. Again, it doesn't matter which one you choose. Well, let's go back and look. What are my pairings going to be, right? If we're using the upper right-hand one, you're going to have positive y and positive x, right? If you're using the bottom one, you're going to have negative y and negative x, right? So you need to make sure that you choose accordingly. So we choose accordingly. Okay. There we go. Okay. The overall equation that we are always trying to use here, right, is our relative acceleration equation, which we can rewrite for accelerations as we already figured, so this is the reason why we're going after what we're going after, right? What are we going to be able to get out of this, right? We should be able to get an x direction equation and a y direction equation out of this, right? Because what are we looking for overall? We're looking for a sub d and we're looking for alpha, right? So I need two equations when I have two unknowns. If I plug in everything and break it into components, if I plug in my things and I break it into components, in the x direction, we know that we have AD, right? It's just completely in the I. That has to be equal, that's negative, negative AD. Why is it negative? We're choosing it to be pointing to the left. I can plug in my other I direction components. This is my x direction equation, or my I. Here's my y, or j direction equation. I have no acceleration at point D here. And I just put all my j direction components. Should be alpha BD, BB. Okay. 617. You can solve these simultaneously. Right? You solve the bottom one first for alpha, right? You can solve this bottom one first for alpha. We'll get in the k direction. And then we plug alpha into the first equation and we'll get AD out. Okay. Graphically, right? Because the book is always talking about, doing these things with these acceleration and vector triangles, right? So the acceleration of point B looks like that, and the acceleration of point D looks like this, right? And so remember, that means that the acceleration of D with respect to B looks like this. And what we're trying to do here is we're trying to make sure I do this right. Right? We're breaking this green one down into that right triangle. Right? That's all we're doing. And here, that's 13.95 degrees, because this angle is also 13.95 degrees. There we have it. these problems are going to start getting long. Right? These problems are going to start getting long. Typically, what you want to do is you want to solve for the velocities first, right? And then follow on to the acceleration. You need to know something about the angular velocity if you want to know about the normal acceleration, right? That's what the equation tells us. So if you're asked to find a normal acceleration or an acceleration in general, for general plane motion, you need to use the relative equations, right? So let's try another one. Try another one. This is similar to one that we've done already as well. All right, why? Remember, this is that rack problem we did in class the other day. And so the center of a double gear has a velocity and an acceleration to the right of 1.2 meters per second and 3 meters per second squared, respectively. The lower rack is stationary. Determine the angular acceleration of the gear and the acceleration of points B, C, and D. Okay, so we talked about this a little bit when we did the problem last time, but just to refresh your memory here. If we needed to describe, the change in translational position, right? So this rolls, right? This is going to roll. And if it was to roll one revolution, how far would it go? If I took a wheel and rolled it on the ground, and I rolled it one revolution, what linear distance would it have to travel? Circumference, exactly, right? So we can say that because, right, we derived this back, I think it was Tuesday last week. It was either Tuesday or at the beginning of class on Thursday. I think it was Tuesday last week. Or, sorry, Wednesday last week. Right. Turns out that you can say this. Why? Well, if I travel X distance by going 2 pi r, right, which is my circumference, then I can figure out the angle that I've traveled through, right? In 360 degrees. Right? Why is it negative? Well, that angle is going to change this way, right? So it's just going to be a negative angle that we're putting in. Okay. But if we do the multiplication of that, right, and solve it for x of a, we get to here. Now that's important, right? Because anytime that we have something that's rotating, that's rolling, right, we can figure out what angle have I traveled through, and how does that relate to the linear distance that I've traveled, right? So let's draw a better picture of this that's a little bit clearer. It's annotated pretty well. Call this A, and that's R1. Here's my other gear here. It's going to have radius 2. Sorry, I flipped those, right? Actually, the inside one is radius 1 and the outside one is radius 2. Here's my coordinates, right? Standard Cartesian coordinates. I've got some rack up here. The one on the ground is stationary, right? So that's the stationary ground. I've got some point here, B. Let's say this is point D, and then this point where we interface here is point C. And there's some velocity and acceleration pointed this way. And we've got some omega and some alpha, about point A. And point A is the center point. Right? So we need to find the linear distance traveled. We just talked about that. It's going to be this, right, R1. Why are we using this? I believe this is a question that Zach asked, right? Why are we using R1 and not R2? That's a good question, right? And the reason we're using R1 is because we know that the ground is not moving. The rack at point B is moving, right? And so you need to take into account the relative velocities of VA and VV when if you wanted to use R2. Since we know the ground isn't moving, that's a stationary point that we can measure against, right? So that's the ideal choice here. If I take the derivative of this with respect to time, I can get the velocity of point A. And if I take the derivative again, I can get the acceleration of point A. So the question was asked, what is the angular velocity and the angular acceleration? Right? That's part of what we have to find. Well, really the angular acceleration, right? But we can find omega because that's going to help us later. Omega is just the velocity of A divided by R1, which is 1.2 over 0.15, which is 8 radians per second in this direction, or if we wanted to write it as a vector, negative 8k radians per second. Okay, solid. We don't need this right away, right? But we were asked to find the acceleration at a point, right? And remember, that means we're probably going to need the normal and tangential components, right? And if we need the normal component of the acceleration, we need omega. So it's finding it up front. How do we find alpha? Well, we're going to rearrange this equation right here to find alpha, right? Alpha is equal to the acceleration of point A over R1. Well, I know the acceleration of point A, right? We were told what it was. We were told that it's 3 meters per second squared. So this is 3 over 1.5. Sorry, 0.15, not 1.5. 0.15, which gives me 20 radians per second squared. This is also going to be in this direction. So if I wanted to write it as a vector, it'd be negative 20k. Remember, k is the z, right? When we're talking about rotations, the way of reading this would be, this is negative 8 about the k-axis, right? So this is rotating around the k-axis, right? It's not pointed along it, it's rotating around it. And that's part A, right? Part A was just to find alpha. We're good. We can solve for it directly. The next part is trickier, right? Because we need to find the acceleration of point B, point C, and point D. Do you guys have any questions on this part so far? Is this all right? Yeah? Maybe? Any questions? Alpha is the angular acceleration. Alpha is the angular acceleration. Any other questions? Okay. So we need to do the next part, right? What's the next part? Next part is we're going to draw donuts, right? It's double. It's a double here. What am I doing with this? Well, I'm going to draw something, right? What do I know here? Well, this is point A. This is point B. This is C, right? So B, A, B, C, and D, right? Those are given to us. I know the acceleration of point A, right? That was given to us at the beginning. So I'm going to assume that this entire system is all translating by A sub A, right? So this is general plane motion, right? It is rotating and it is translating. So I'm going to take this whole thing and I'm going to, just like we did with our wheel on the whiteboard, right? I'm going to pick it up and I'm just going to slide it and put it down where it's supposed to finish, right? Then I'm going to look at it and I'm going to rotate it about point A. And if I rotate it about point A, I use a different color, so it's not. I'm going to apply some omega and alpha here about the center point. And when I do that, I'll end up with tangential and normal components for AB with respect to A at point C. And at point B. Remember, the normal component always points back toward the center of rotation. Always. The tangential is always tangent to the path at that point. I made some assumptions here, and I assumed that my acceleration would be moving in such a way that that alpha would be created, right? So we would maintain a rotation, an angular acceleration in the clockwise direction. What is this going to equal? We'll fill in the back half of this in a second. And we'll fill in the final state in a second. What's important here is that we have to do this portion, right, which we already know. That's just going to be 3. Everything's going to move by 3. And then we have to do this portion, okay? So let's focus on the rotational aspect of this, right? Why don't we start with point B, right? So we're going to start with point B here at the top of the central pulley, right? For point B, the equation, right, if I want the acceleration of point B, this is going to be the acceleration of point A plus the acceleration of point B with respect to point A, which I'm going to break down into my normal and my tangential components. All right. So in this case, right, what's my tangential component, right? We know what AA is. AA was given to us. Well, my tangential component is alpha about the z-axis cross R of B with respect to A. And my normal component is omega squared R B with respect to A. These are vectors. And so we're going to have to do some cross product math magic. Right? Okay. Just going to rewrite this equation on the next slide so there's a little more room. So this is the equation we're trying to construct, right? This is what we need. So we need alpha K cross R of B with respect to A, right? So if we have A sub A here, this is what A sub B looks like. And so we can construct some tangential and some, oh my goodness, this pen is killing me today. And some normal component. Okay. That's just what it looks like, right? And this angle on here will be theta. It's not super essential. I am going to leave this here, though. This is important. The IJK circle. Right? I cross J, positive K, J cross K, positive I. If you go the other way, I cross K, negative J. Right? Okay. So what do we know? Well, first of all, I know the acceleration of A, right? That's 3I. We were told that's what it was. I'm going to go back to my drawing here. I'm going to ask you guys a question. How do we find R of B with respect to A? If you're at, remember, that is asking you, if I'm standing at point A, how do I get to point B, right? Tell me the direction in a vector. Right? If I'm at point A, how do you tell me to get to point B? How far do I have to go to get to point B? And in what direction? Right, say that one more time again. Right, which radius? R1 or R2 to get from A to B? R1's the bigger one. I know my handwriting is garbage. It's R2, okay. So which direction? Is it X direction or Y direction? Right, so you'd have to go R2 in the positive Y direction, right? You have to move positively from there. Okay, so that's going to be point 1 in the J. Okay, so we're going to, oh, too far. No, did I skip it? In one sec, this is going to trigger me. Apologize, please stay on the line. Your call is important to us. There you go. Okay. So we are, right? We've got 3I plus negative 20K, right? Because we found alpha already, and we found that alpha was negative 20K. Cross, well, Miguel just told us that this is just 0.1J, right? Minus omega, well, we found omega, right? That was just 8. And so we can take this cross product. Yeah, we can take this. Let's do this. I'm gonna write my 3I. What's this cross product? Do I have to do the whole columns and thing? There's only 2 things here, right? So this is K cross J. K cross J gives me negative I, right? In this case, we'd have to take K cross J, right? K cross J is going to give me I, but it's going the wrong way. It's going against the circle, right? So that would give us a negative I. Negative 20 times 0.1 is negative 2 times negative I, right? Gives me plus 2I. Let's do it out with our other method just to check. 0, 0 minus 20. 0.1, oh, sorry. 0.10, right? Cover up the first column. Now what do I end up with? For I, we'll get I. And I'll get 0 minus negative 20. If I cover up the J column, I get 0 times 0 minus 0. And if I cover up K, I get 0 minus 0. So this is just going to be, no, sorry. Oh, Dr. D, what are you doing? Trying to prove what I just wrote down, not disprove it. All right, so you cover up I. What do you get? You get 0 minus negative 20 times 0.1, right? Cover up I, I'm left with 0, cross 0, minus 0.1 times negative 20. Remember, cross product is this times this minus this times that, right? Great. That gives me 2R. Right? That's where that comes from. That's how it works. Great success. All right. Cool. We're going to review cross products more in depth later today in class, if you guys are still feeling weekend. So. What about this one? Negative 8 squared times 0.1. Well, that's going to be 64 times 0.1. So minus 6.4 in the J. Right? So we can rewrite this as 5I minus 6.4 J. Meters per second squared. That's the acceleration of point B. Okay. So keeping track of our vectors is really important, right? If we keep track of our vectors really well, then a lot of this, the cross products and stuff, kind of fall out. You could also write this in terms of the magnitude and the angle, right? What's the magnitude? Well, that's going to be the Pythagorean theorem. What's the angle? What's this? Maybe 52 degrees down. So remember, this is telling you that I've got an x component like this and a y component like that. So really like that. That's the angle, AB. In there. We can do the same thing with the acceleration of point C. Okay. Still using AA. And now we just have to shift everything to be in terms of C with respect to A. Right? So we can do this. All right. It turns out it's the same equation that we have written at the top there, except we're changing all of our B's to C's. Right? We're going to change all of our B's to C's. Alpha doesn't change, right? Everything is still spinning with the same alpha, and omega doesn't change. All of these things have the same axis of rotation, and we'll be spinning with the same alpha and omega. So the only thing that's changing is R of C with respect to A, right? So how do we get to C from A? Right, so let's go back and we'll look. If I'm standing at A here, I'm standing at A, give me the vector to get me to C. Right, so I need a magnitude, so right, I need a distance, and I need a direction, right, X and Y. So how do I get there? How do I go from A to C? How do we go from A to C? How do I go from A to C? Yes, how do I get there? Positive or negative? Yep, yep, negative R1 in the J. Right, that's the vector. It goes straight down, straight down. So we can plug this in, right? So I'm going to have 3I plus, plus negative 20K cross minus 0.15 J minus 8 squared times 0.15 times negative 0.15 in the J. That's what I'm going to have. Okay. Okay. So we do that cross product again. And we can do this cross product again. And so number 3I plus, well, K cross J. We'll put a box around this so we don't lose it. So K cross J gives me negative I, right? K cross J gives me negative I. So I've got negative 20 times negative 0.15 times negative I. That's going to give me minus 3. 20 times 0.15 is 3, right? Then the negative I gives me a negative plus, well, 64 times negative 0.15 minus that, that's going to be 9.6j. So something interesting happens here. No, that goes away. Or this is just 9.6j. Right, so there's no tangential component of my acceleration at the bottom of my wheel where it hits the ground. And this is what we call the no slip condition. This is the no slip condition. And then we got one more, right? We've got to do point D. You guys thought that it's the same exact equation that we've been using. We're going to switch all of our B's and our C's to D's, then it's exactly what we're going to do, right? Rather than me, we're going to do it. I'm going to take us back up to the original drawing. Right, this means that I'm going to need R of D with respect to A. So if I'm standing at point A, how do I get to point D? Yep, it's R1. Is it X direction or Y direction? X, is it positive or negative? All right, so you got negative R1 in the I, right? Negative R1I. Perfect. Leave this here again. So negative R1 times I is my R of D with respect to A, right? So this is going to be 3I plus, well, alpha is negative 20K cross 0.15 I minus 8 squared. This is negative, right? Negative 0.15. I apologize. That's negative. Okay. Well, that's certainly something. What happens? Well, we get 3I plus, well, K cross I gives me positive J. So that's going to be 3J, right? 20 times 0.15, if they're both negative, the negatives cancel. We're left with 3. K cross I is going in the appropriate direction of our circle, so it will give us positive J. 3J. Plus 9.6 I. Right? 64. Negative 64 times negative 0.15 is 9.6 in the I direction this time. So we can rewrite this. A sub D is equal to 12.6 I plus 3J. All right, in meters per second squared. So the magnitude is 12.95 meters per second squared. And the angle of A sub D is 13.39 degrees. Up and to the up and to the right. Again, these are going to be longer, these problems, right? We're going to start getting a little bit longer. There's a lot of stuff we could do on a quiz or an exam, right? If you left it as the vector, like 12.6 I plus 3J meters per second squared, that is fine. I don't need right? Writing it as the magnitude and the angle is good as well, but it's just another way of showing the vector, right? If you wrote it in a vector notation with I and J, I'm fine with that. You guys have any questions on this one? Doing all right. No, nothing.
So I would sometimes use just I and K and then also.
Okay. So the rotational quantities like omega and alpha are rotating about the z-axis. Right? So if we think about this in 3 dimensions, right? I know we're only drawing 2 dimensions here, right? But in 3D, we have something that looks like this where we'll call this I, we'll call this J, and we'll call this K, right? And the way that where this gear exists, we're looking at it, try to draw this in 3 dimensions, right? I'm going to try to draw one part of it, right? Yeah, that's not too bad, right? We're looking at this gear straight on, right? Just in the XY plane. So it's all rotating about that K axis, right? So when we write our vector, alpha is around the z-axis, it's about K, right? So that's why there's that K there. In terms of the position vectors, right, this is a direct mapping of how far do I need to go in the I and the J? How far do I need to go in X and Y if I start at a certain point and I'm going to another? Okay, so that's why we use those quantities in the way that we do. That's why we use I, J, and K the way that we do. When you're taking a cross product, right, what you're really doing is you're saying, I have 2 vectors, and I want to know where I need a third vector that's 90 degrees to both of these vectors. Okay. So we know that I and J, right? We know that X and Y axes are 90 degrees to one another. So if you take the cross product of those 2 axes, you'll get the Z axis, right? You get the K axis. That's the basis for the right-hand rule, is really just us doing cross products. Okay. That kind of answer your questions there? It's just it's the vector notation. I think it's easy to understand in 2D when we're talking about, translational movements. When we're talking about rotations, you're being told what axis we're rotating around, right? So you'll see when we do some other problems later in the semester, when we start talking about like gyroscopic rotations, that we'll have to account for rotations about more than just one axis. But for the short term, right, we're going to focus mostly general planar motion where we have rotation only about one axis. Any other questions? No? Maybe? We got a homework due and a Learn Smart due. That's Sunday. Don't forget to vote next week. Not part of your, I guess I could make it participation next week, right? You have to come in and show me your vote sticker. Right? Well, if you already voted by mail though, right? I already put my sticker on. I wore it around last weekend. Felt super cool. I'll do it. Vote. All right. So let me ask you this, right? Let's go back to this problem. If the clockwise angular velocity of crankshaft AB is constant, which of the following statements is true, right? So the crankshaft velocity omega of AB, that first part, is constant, right? So then what else is true? A, the angular velocity of BD is constant. You need to show hands, right? Who thinks it's A? B, the linear acceleration of point B is 0. That's B. C, the angular velocity of BD is counterclockwise. Thinks it's C. And D, the linear acceleration of point B is tangent to the path. So who's got A? Yeah, one through them again. All right, who's got B? Who's got C? And who's got D? All right. C. So what happens, right? Let's look. I got these two things. This one's going to be rotating this way. As a result, the other one's going to be rotating the opposite way, right? It's kind of like how gears work. One's rotating one way, the other one's going to rotate the other. All right. So now this is the part. This is some fun stuff. We're going to talk about rotating frames today, and then general motion. General motion is the 3D variant of general plane motion. I'm going to go over it today, but we're going to stick mostly to simplifications that allow us to talk about general plane motion and do the problems like we've been doing. When we add a third dimension, things get a little bit wonky. And we'll talk about what I mean when we get there. All right, but first, let's watch a video about rotating frames. Oh, shoot. Sorry. Technical difficulties. And by that, I mean, I hit the button by accident. Hit the button again. Let's stop hitting the button.
Today we're going to take a trip to the playground in order to observe moving reference frame kinematics. We're going to participate in a seemingly simple event, passing a ball across a common playground merry-go-round. And we're going to see some strange yet predictable effects that arise from the moving reference frame. In our first shot, the camera is attached to the ground in the stationary frame. Notice that the ball travels in straight lines. In our second shot, the camera is attached to the merry-go-round, rotating. Notice that the ball curves to the left on every pass. Let's try to explain what we just saw. First, a minor point is that the velocity of the ball in the stationary frame is the relative velocity imparted plus the velocity of the person pushing the ball. This determines the direction of the velocity. The more interesting results are in the rotating frame. As far as the curved path goes, it can be explained by the Coriolis component of acceleration seen in the moving reference frame acceleration equation. We assume that the merry-go-round has a constant angular velocity, and the ball begins with the velocity relative to the merry-go-round, vrel, towards the center of the merry-go-round. Since there is no net force on the ball, we assume its acceleration to be 0 in the stationary frame. In the rotating frame, we attach our observer a set distance above the center of the merry-go-round, approximately where our camera is located. When we set up our acceleration equation, we see a number of terms drop out as zeros. Now we solve for the relative acceleration in the moving frame. We see that it involves a component that will always be in the radial direction, resulting from the ball not having the same centripetal acceleration as it would to stay on that point on the merry-go-round, as well as a term from the Coriolis component. This component will always be normal to the relative velocity, and thus cause a curve. From the cross product, if the merry-go-round is rotating clockwise, the ball will appear to curve to the left. Finally, we will show what the relative acceleration is when the ball is initially released. As you can see, there is a term for the lack of centripetal acceleration in the x direction, as well as the Coriolis component that causes the curve in the y direction. Given this information, we would expect the path to look as shown. Knowing this, let's look back one last time at the video. As strange as the path may seem, it actually follows what our moving reference frame kinematics equations would suggest. Generally speaking, rotating reference frames can offer some very interesting and counterintuitive phenomena.
So rotating frames, right? Let's talk about this. So sometimes, like in the playground example that we just watched, right? Your reference frame is actually moving. We talked a little bit about this, right? In the real world, this is kind of like when you're trying to land your helicopter on the floating pad, right? On the ocean. That reference frame is moving, right? In this case, what if we have something that's not translating, but a reference frame that rotates, right? Why is this realistic in real world? Well, the Earth, right, depending on your beliefs, right, but the Earth rotates about its axis at a constant speed, right? So technically, we are always on a rotating reference frame. Now, I realize this is controversial because this outs me as a round earther, right? And all that, right? But, just throwing that out, right? So what do we have going on here? This picture is somewhat complicated to look at, right? So what do we have? We have this black reference frame, the capital XYZ, right? And so when you see frame O, capital XYZ, we're talking about this black one, right? We're talking about the black reference frame. Okay. The lowercase XYZ is the red reference frame. Okay. OXYZ. And that rotated, right? And this one is fixed in space. This one will not move, it will not translate, will not rotate. This one can spin around point O. And it can do so in 3 dimensions. Right? So it can get pretty crazy pretty quick. Right? And it has an angular velocity that's described by capital omega, some vector capital omega that tells you how much it rotates about the x, the y, and the z axis. Q is a vector function that varies in direction and magnitude. Right? And notice what Q is. Q is perpendicular to our reference frame. Right? So with respect to our rotating frame, the red frame, we get something that looks like this, right? We can say that Q is X, Y, and Z components according to the red frame. Okay. So let's notice, right? I want you to also notice we've got our unit vectors pointing along the red frame, right? The rotating. Okay. So great. So we can take Q dot, right? If we take Q dot and we want to find it with respect to the non-rotating frame, well, it turns out that then we need to not just take the derivative of Q, right? Because I, J, and K are not fixed to the black frame, they're fixed to the red frame. So I, J, and K can change if we're looking at it from our fixed reference. Okay, so if we do that, right, the punchline here is that we get this on the equation here, Q dot is equal, Q dot for my big reference frame, for my fixed frame, is equal to the Q dot of the rotating frame plus omega cross Q, which is kind of like what we were talking about in the video. But what is Q? Q is just some parameter that we're interested in, so we can really use it for anything, right? So what about planar motion relative to a rotating frame? Because in 3 dimensions, I really do think that this is a very difficult concept to wrap your head around, right? This is something that it's not super intuitive. right? So let's simplify it down to just rotating about a single axis, right? So we have our merry-go-round at the playground, right? That's just spinning around one axis, right? So we're using that example, right? So in this case, the black reference frame is capital XY, and the red one is my rotated frame again, right? And notice I've got some point P up here, right? That's some point P. Now that vector R, the vector R goes from the origin to P, and both of these frames share the same origin, but depending on whether I'm in the red one or the black one, that vector is going to be slightly different, right? That vector will have different coordinates based on each of those frames. Right? The frame is rotating with a velocity of capital omega, right? The position vector of the particle is the same in both reference frames, but changes depending on your choice of frame. And so we can talk about the absolute velocity of that particle, right? And so think about it this way, right? If we're talking about the merry-go-round with the ball, right? That's spinning. So that's giving our ball some velocity as well as us rotating, right? Which is why you see it curve as we pass it, right? So if we want to take into account all of the velocity components for everything, we need to use this equation, right? The velocity of some point P is equal to the velocity vector from the not rotating frame plus the amount of rotation that we see. Okay. So we're gonna talk about this on the slab now. So if we have this rigid slab, it's attached to a rotating frame, right? So the slab is rotating, and that XY, right? This red frame is describing the rotation of our actual object, our actual slab. We're going to call frame OXY. We're going to call it that script F for short. So whenever you see that in the book, they're talking about this guy. They're talking about a rotating frame. So we can use what we know about rigid bodies to figure out what the velocity of point P is, right? Because the velocity of P with respect to the rotating frame is just R dot O lowercase x1. So how does this vector change if we're looking at it from the red reference, okay? And then VP prime is how does the velocity of this particle, what does the velocity of this particle look like if I measure it in black? Right, so I'm taking both reference frames into account and I'm adding those results together. Right, so VP is equal to VP prime plus VP with respect to the rotating frame. This is very similar to our relative velocity equation, right? Except in this case, we're relating the two reference frames to one another, so we're saying there's some velocity that we take into account from viewing this from a fixed reference frame, and there's some velocity that we're getting from the rotation. Right? And both of these things need to be accounted for to get the total velocity of some point on our rigid line. We can do this, we can take the derivative of this, right? So we can rewrite VP, right? Let's do that first. Let's rewrite VP. Right, so VP prime, right? The velocity of that point is just the angular velocity of my slab cross R, right? Because it's the tangential velocity of this point on my rigid body, right? Plus R dot OXY. Plus how R is changing with respect to the rotating frame. Okay. If I wanted the absolute acceleration for a particle, well then, guess what? I just take the time derivative of that velocity equation. And it gets gross, right? It gets kind of gross. And we can step through it, right? We can make some substitutions, so we can figure some things out. So it turns out that AP prime in this case becomes omega cross r plus omega cross r. That looks a lot like my normal and tangential velocity equations, right? Is it omega cross r just my angular acceleration when we use lowercase? Well, in this case, it's just the velocity of the frame. Omega cross r is some normal acceleration. And then we have the normal, the r double dot, right? So how is this r changing with respect to the rotating? We can rewrite this whole thing like this here. Okay, and so there's one term that we haven't discussed yet, right? We've got, this is AP with respect, right? So that's this guy right here. We've talked about this front part, but what is this extra piece in the middle? Now that is what we call the Coriolis acceleration. Okay, the Coriolis acceleration is 2 times omega cross r. What is the Coriolis acceleration? Well, they said in the video, right? The Coriolis effect, or the Coriolis acceleration, is the extra bit of velocity that we get from actually being on a rotating frame. And it's going to be normal to the frame. In the real world, we talk about, sometimes it gets talked about, most often it gets ignored. Coriolis acceleration due to the rotation of the Earth. There is a Coriolis acceleration due to the rotation of the Earth. When is the time that you would see this practically? If you fire a gun straight up into the air, there is a reason why the bullet will not come down and hit you in the head. And that is the Coriolis acceleration, right? Because as you fire it up, the Earth is rotating and that's going to move it. So there's that. I don't suggest trying it. It's probably not a great idea. But if you ever end up doing any work with targeting systems, depending on where you are on the globe, right? There's that word again, the 5-letter word, the G word, people don't like, right? But if you're anywhere on the globe, your Coriolis acceleration changes depending on how far away you are from the equator. And so naval vessels have correction factors built in to their targeting systems that take that into account. It's not a huge amount most of the time, but it can get bad the further away you get from the equator. So that's the equation, right? This is the equation. If we have a rotating frame, this is the equation that we want to use, right? In general, we can always use this equation. If we don't have a rotating frame, what happens? Well, this just goes away, right? The Coriolis term goes away, and this r double dot goes away, right? If you don't have a rotating frame, this is the equation we've been using, that's with lowercase omega, right? So we just have a couple extra pieces due to the rotation of the frame. Right? It's the same equation we've been using, but with a little bit extra. That's all it is. So we're going to step through this one, and we're going to see where this takes. So we've got this collar on a bar, and notice it's not stopped, right? This isn't connected with a cord or anything, right? This could slide off as far up or down as it wants, right? So this distance r can change, right? This distance r can change with time. So there's some velocity associated with this along the bar, right? So consider the collar P, which is made to slide at a constant relative velocity u. So we're saying that this u is the velocity of P along the bar, right? The rod is rotating at a constant angular velocity omega, and the point A on the rod corresponds to the instantaneous position of P. So at this moment, P, the collar P is at A. We want to find the absolute acceleration of the collar. So the acceleration of P, the collar, is equal to the acceleration of point A plus the acceleration of point P with respect to the rotating frame plus the acceleration of due to the Coriolis, right? Coriolis effect, the Coriolis acceleration. That's the equation that we just wrote on the previous slide, right? It's right here. It's just this. AP prime here is just A of A. Right? P prime is just defining the point on the rotating frame that you are at that instant. In this case, we know that that is A. We know that that's A. We also know a couple of other things. First off, we know that the acceleration of point A is going to have a normal component, and it won't have a tangential component. Why do we know it won't have a tangential component? Because omega, the angular velocity of the bar, is constant. Remember, the tangential acceleration is dependent on alpha. Alpha in this case is 0. And so here's our equation. We also know that the Coriolis effect is going to accelerate this to the left. The acceleration of A is just our standard normal tangential components, right? So it's omega cross R plus omega cross omega cross R, or sorry, omega dot. Here this is, omega dot cross R. Omega dot cross R. Well, we just talked about this, right? Omega dot, omega is constant, right? So omega dot goes away, 0. And we're just left with omega cross R, which is R omega squared. R omega squared.
System will,
That's that script F. That just is telling you that it's with respect to our rotating frame instead of our normal frame. So that's just a script F. I don't know why the book decided to use a script F, but that's what they decided to use. It's just the acceleration of point of the collar here of point P with respect to the frame. So what does our rotating frame look like at this instant, right? Right, something like that. All this X and this Y, right? It's rotating. Our non-rotating frame, right? Our Cartesian frame, our Newtonian frame. I don't know why I put X up there. Dr. D's not having a great time right now. Here's Y. These are capitals, right? Capital X, capital Y. I know it's not drawn great, right? But this is the idea, right? So let's go back to our equation on the other page. So we need AP prime, or A sub A, which we just figured out. We need A of P with the acceleration of P with respect to our rotating frame. Well, that's just going to be that R vector in our rotating frame. Take the derivative of it twice, right? R double dot O X Y. Well, we're told that U is a constant relative velocity along the rod, right? So if U is constant, then this has to be 0 as well, right? So that's good. And then the last part is the Coriolis acceleration. The Coriolis acceleration is 2 omega cross V P with respect to the rotating frame. We know what that is, right? We know this V sub P with respect to the frame because we're told, right? It's U. That is the relative velocity of the collar with respect to the bar. And we're just substituting in lowercase omega for capital omega. Okay. So that's what we're left with. So if we add up R omega squared plus 2 omega U, right, we'll get some vector for the acceleration of point p. Right? We can write that in terms of our global reference frame, the black one, capital X, capital Y. Right? Another way of thinking about this is we have radial and tangential vectors. So break it down into pieces. Think about what we know, right? Okay, so let's think about this. We're going to try to break this down a little bit more. It's the same problem. So what happened, right? This first position here, the faded one, that's state one, right? And at some other time, we'll call it sometime delta t, right? It's going to move, and it moves to the next position, right? Right. So this one here, right? Let me do this. This dashed line, right, we'll call this x. We'll call this y, right? That's my rotating frame. And then at some other point in time, now we're here. X prime and y prime, right? Remember, this rotates, right? And the angle that this is rotated through, we're going to call that delta theta. Right, so at time t, we have some velocity, right, which is equal to the velocity of point A plus the relative velocity of the column. And at some point, t plus delta t, we're left with v prime plus va prime plus v prime, right? So we're tracking the velocity of that point A, right? And A and A prime are just where P is on the bar at that instant. Okay. The change in velocity over time is represented by the sum of three vectors. Okay, so look at the picture up over here on the right. Okay. Originally, I have u, right? That vector from O prime. Let me color code this a little bit. So originally, this guy from O prime up to R, right? That's my original velocity. Okay. But we're going to rotate through some angle, right? And in order to get this part of the velocity, I need R prime, right? So R prime plus T to T double prime plus T double prime to T prime, right? So we have this component here. We've got this component here. And that component there. I know the green on green is not easy to see. So this is representing the change in my velocity, right? And I've got some x component change, I've got some y component change. Remember, we're talking about the absolute velocity here, right? Talking about the absolute velocity. So we have to take into account all of the velocity that we have, right? T double prime is due to the change in the direction of the velocity of point A on the rod, right? We can take the limit of T double prime divided by delta t as time goes to 0, and that's going to equal the limit of VA delta theta over delta t, right? Which gives us R omega squared, which is just A times A, or A sub A. Hey, we already figured this out. R prime and T double prime T prime result from the combined effects of the relative motion of P and the notation of the rod. The rotation of the rod, right? And look, we'll end up with 2 omega times u, which is my Coriolis portion. Okay, so this is just a proof of the equations that we use, right? Using a slightly different method where we're just tracking the change between 2 points, right? Just tracking the change between 2 points. All right. Let me ask you a question. You're walking with a constant velocity with respect to the platform, which rotates with a constant angular velocity omega, not W, omega. At the instant shown, in which direction will you experience an acceleration? Choose all that apply. Okay, so you're walking, you're the purple dot, right? You're walking straight ahead, walking in the positive J direction. There's a rotation that is counterclockwise. Which way will you experience the acceleration? Choose all that apply. You guys think that you will feel an acceleration in the positive X direction? Who thinks the positive X? Who thinks the negative X? Who thinks positive Y? And who thinks negative Y? Who thinks the acceleration is 0? So negative X direction. You're going to feel like you're getting pushed to the left, or you're going to feel accelerated to the left. Also, the negative Y direction and pulled back. You're going to be pushed back. Why? It's the same reason. It's the same stuff that happened to that bar, right? We had a bar that was traveling with a constant omega, right? We have that Coriolis effect that's pushing us left, and we have some normal acceleration that's accelerating us back towards center. There's our equation. Omega is constant, so omega dot and r double dot are going to go away, right? Because you're walking with a constant velocity, and omega is constant, so omega dot and r double dot are going away. So if those go away, we're just left with the Coriolis and the normal acceleration. Don't take my word for it. Let's watch another video on rotating frames.
Here you see footage of hurricanes that formed in the Atlantic Ocean during 2009. Do you see that every single hurricane rotates counterclockwise? All hurricanes formed in the Northern Hemisphere rotate counterclockwise. In this video, we'll provide you with the tools to explain why hurricanes rotate the way that they do. This video is part of the Representations video series. Information can be represented in words, through mathematical symbols, graphically, or in 3D models. Representations are used to develop a deeper and more flexible understanding of objects, systems, and processes. Hi, my name is Sanjay Sharma, and I'm a professor of mechanical engineering at MIT. Today, we're going to demystify the origins of the forces that appear to act on objects in rotating frames. Before watching this video, you should be familiar with how to define basis vectors, inertial and non-inertial reference frames, and the representation of rotation rates as vector cross products. After watching this video, you'll be able to explain why centripetal and Coriolis accelerations arise in rotating frames of reference and apply your understanding of the Coriolis acceleration to determine the direction of rotation of hurricanes. A frame of reference is a choice of coordinate frame, a set of orthogonal basis vectors. The frame is allowed to undergo rigid body motions. Rigid body motions include translation, rotation, or a combination of translation and rotation. As a frame of reference undergoes a rigid body motion, the three basis vectors retain their original length and remain mutually orthogonal. In this video, we're going to focus on rotating frames of reference. In particular, we want to think about frames that are rotating with constant angular velocity and that aren't translating. Rotating frames of reference are non-inertial, thus we detect fictitious forces in them. We're going to explain how these so-called fictitious forces arise. This is a turntable. We say that we are in a turntable frame of reference because the camera is mounted to the turntable. From this frame of reference, it appears that the turntable is stationary as the world spins around us, despite the fact that our experience tells us that it is the turntable that is spinning. Here, you see an orange disc attached to the turntable by a string. If we rotate the turntable quickly enough to overcome the friction between the disc and the turntable, you notice that the string becomes taut. Newton's second law implies that there must be a force equal and opposite to this tension force for the disc to remain stationary. This apparent force is what we call a fictitious force. Let's rotate the turntable with two discs. One is attached to the table by a string, while the other is unattached. The fictitious force causes the unattached disc to fly off the turntable. Is there really a force? If so, where does it come from? Pause the video and discuss. In addition to the turntable frame, there is another frame of reference that will be useful in our analysis. This is the ground frame, G, which is any coordinate frame that appears to be stationary while standing on the ground. The turntable frame, T, refers to any coordinate frame that appears stationary while standing on the turntable. From the ground frame, the T frame is rotating counterclockwise with a constant angular velocity, or almost constant angular velocity. It is important to be explicit about the particular frame of reference used to describe a velocity or acceleration vector. The velocity of the stationary vector is 0 in the G frame, but the velocity of the rotating vector is 0 in the T frame. We will denote the frame of such a vector by using a left superscript, G or T, to designate if we are considering the vector as an object in the G frame or the T frame. In the T frame, the position of the disk is fixed, so its velocity and acceleration are both 0. Pause the video here to determine the velocity of the disk as seen from the ground frame.
What would it be? I'm not going to pause it.
According to the G frame, the T frame is rotating with some angular velocity represented by the vector omega. Omega points along the axis of rotation with magnitude equal to the angular velocity. The velocity of the disk according to the G frame is entirely due to the rotation of the T frame and thus can be represented by omega cross r. Recall that in general, any object that is moving on the turntable will have a velocity that can be defined in the T frame. The velocity in the G frame can be found as the sum of the velocity in the T frame and the velocity that arises due to the rotation of the T frame with respect to the G frame. We can think of this as a rule for taking the time derivative of the position vector r in both the G and the T frame. We can generalize this formula for how to take the time derivative in the G frame of any vector x in terms of its T frame derivative. This formula holds when the T frame is rotating, but not translating with respect to the G frame. Use this formula to take the time derivative of velocity. Try to find the general formula for the acceleration in the ground frame in terms of the acceleration in the turntable frame and various other terms. Pause the video while you carry out the computation. Looking at this formula, the first term is the object's acceleration as observed in the T frame. The remaining terms can be thought of as giving rise to fictitious forces which cause the acceleration observed in the T frame. The second term is due to the angular acceleration of the T frame with respect to the G frame. The third term is the Coriolis acceleration. Note that it depends on the velocity vector of the object in the T frame. And this last term is the centripetal acceleration. Observe that it depends on how far the object is from the axis of rotation. Given this information, pause the video and determine the acceleration of the orange disk in the ground frame. The velocity and acceleration of the disk are zero in the t frame of reference. We did our best to rotate the turntable in this video with a constant angular velocity, so we will assume that the angular acceleration is negligible. Thus, the acceleration in the g frame is given completely by the centripetal acceleration term. This vector points in the negative r direction, with the magnitude given by the distance from the axis multiplied by the angular velocity squared. In the g frame, which is inertial, we do not observe effects of the so-called fictitious forces. Remember, the disk wants to move in a straight line. It doesn't want to turn. The string imparts a tension force upon the disk, which provides the centripetal acceleration needed for the disk to rotate with the turntable. But in the non-inertial T-frame, we may think we observe a fictitious force. The only thing that is fictitious is your perception that the disk is not accelerating. It is a physical illusion created by the fact that from the turntable frame of reference, you don't observe the centripetal acceleration of the turntable. In this video clip, we are rolling tennis balls through a plastic tube. In the T-frame, we observe that the ball moves along a curved path. The curved motion observed in a rotating frame of reference is called the Coriolis effect. Pause the video and explain what you think is causing this curved motion. To better understand what is happening, let's look at the same motion in the inertial ground frame. But first, what do you think the motion of the ball will be when observed from the ground frame? Pause the video and make a prediction. That's right, the path is a rather straight line along the initial trajectory. It is the motion of the turntable that is curved as the turntable rotates counterclockwise. But from the turntable frame, points on the turntable appear stationary because you're rotating with the frame. So you perceive that the ball is curving to the right even though it is you that is moving in a circular path. You might try to explain the curvature using fictitious forces, but we know that these forces are really just accelerations of the turntable frame that we simply do not perceive. Let's use what we know about the G frame to understand what these accelerations are in the T frame. Using the general formula for acceleration in a rotating frame that we found earlier, pause here and determine the acceleration in the T frame.
I just did this one. This is the
Because the velocity is essentially constant in the G frame acceleration is zero. We can arrange the remaining non-zero terms to find an expression for the acceleration of the ball that we observe in the T frame. We find it is equal and opposite the sum of the Coriolis acceleration and the centripetal acceleration. This term is the negative of the centripetal acceleration, which we saw in the previous example. This acceleration is always pointing outwards from the center of rotation. The second term is the negative Coriolis acceleration. This acceleration is perpendicular to the velocity of the ball in the T frame, creating the curvature of the ball's path. We've said the accelerations are created by the rotation of the turntable. How does this happen? For an object to rotate with the turntable, a centripetal acceleration is required. Without it, an object appears to move outwards from the center of rotation. Even more is happening though. Because of the rigid body rotation, the velocity of the point near the outside edge of the turntable is greater than the velocity of the point near the center of the rotation. Moving objects accelerate due to this velocity differential. The acceleration is perpendicular to the velocity of the object. But you don't realize this acceleration exists from the turntable frame because you don't perceive your own rotation. You can feel these accelerations yourself if you walk around a carousel. Or you can try waving your arms or legs on some other rotating theme park ride. Remember, the Earth is a rotating frame of reference. Even though we're used to considering the Earth as a fixed frame, Some phenomena, such as hurricanes, are created by the rotation of the Earth. We're going to use what we learned earlier to understand why hurricanes rotate the way they do. We can model regions of the Earth quite easily. For points that are in the northern or southern hemispheres, but sufficiently far from the equator, we can model the hemisphere by projecting it onto a disk. From this perspective, the northern hemisphere is a counterclockwise rotating disk, and the southern hemisphere is a clockwise rotating disk. Near the equator, we can't model the Earth as a disk. Instead, a better model would be the outside surface of a rotating cylinder. Our understanding of the Coriolis effect from the turntable will directly apply to this model of hemispheres. Now let's start by thinking about hurricanes. Hurricanes are formed when there are small regions of very low air pressure. The existence of this low pressure region causes air from all directions to move towards the low pressure zone. With this information and what you know about the Coriolis effect, explain why hurricanes in the northern hemisphere rotate counterclockwise. As air moves towards the low pressure zone, the air moving from the south veers to the right due to the Coriolis effect. Similarly, air moving from the north veers to the left of the low pressure zone. At the same time, air is constantly pulled in towards the low pressure zone. The combination of these processes creates a region of counterclockwise rotating air. This is why hurricanes in the northern hemisphere rotate counterclockwise. In this video, we saw that in rotating frames, an apparent force pulling away from the axis of rotation is really the object's tendency to move in a straight line. In a rotating frame of reference, objects require a centripetal acceleration to remain stationary in that frame. Moving objects in rotating frames travel in curved paths due to Coriolis acceleration, created by the fact that the velocity of the points in that frame are greater further from the axis of rotation. On Earth, we can observe the Coriolis effect in the counterclockwise rotation of hurricanes in the northern hemisphere. This leaves two questions for you. What direction do hurricanes rotate in the southern hemisphere? And why can't hurricanes form at the equator?
Right. Cool. So hopefully we're starting to see how having a rotating frame can affect things, right? And in certain cases, like the Coriolis acceleration, right? It's not, well, right. Coriolis acceleration can affect things in different ways that aren't always intuitive, right? So let's walk through this problem. I've got this thing here. This is called a Geneva mechanism, right? So how does this work? Typically, you use a Geneva mechanism for timing, right? So what happens is, right, I've got this pin at point P on this rotating disk D, right? And you can see I've got this like sand dollar looking thing here, right? So as this rotates, right, as this rotates, the pin is going to enter that slot, right? It's going to hit here, and it's going to force this sand dollar disk to rotate as this comes around, right? So it'll give it a quarter turn, right? So this rotates this way, and as it rotates this way, it's going to push down here, which is going to cause the brown disk to rotate the opposite way, right? And then once it gets down to this position, right, the pin will exit here, go around again, right? And so every time disk D rotates once, you get a quarter turn on the Geneva mechanism, right? You kind of use this for timing, right? So that's how it works. You don't see them very often, to be quite honest. Right? You don't see these mechanisms very often, but there are reasons why you would want to use them. So disk D of the Geneva mechanism rotates with a constant counterclockwise angular velocity omega D equal to 10 radians per second. at the instant when phi is 150 degrees. So notice we've started here at 135. We're going to do our problem when phi is 150, not 135. So the picture here is not representative of what we're doing. Our pin will be in that slot further, okay? We want to determine the angular velocity of disk S, the velocity of the pin P relative to disk S, and the angular acceleration of disk S, right? So when we're talking about this, right, disk D is a rotating frame, right? P is attached to D, but it's rotating, right? This is our turntable, right? Like in the video, this is our turntable, and there's some pin on the turntable, right? And it's rigidly attached to the turntable, but we want to track how this point on this disk moves with relation to this frame, right? Okay. So let's see what we can do. So there's a couple of things that we know from our problem set, right? So what do we know? First of all, we know omega d is 10 radians per second, right? We know capital R, which was given as 0.05 meters or 50 millimeters. We know that omega d is constant, so alpha d is going to be 0, right? And we're asked to find omega sub s at phi equal to 150 degrees. We want to find v of p with respect to s at phi is equal to 150 degrees. And we want to find alpha of s at phi equal to 150 degrees. So let's draw our picture here, right? So I'm going to just draw a horizontal line to help me, to aid me, right? This is going to be point B. What is point B? Good question. Point B is the center of disk D. Point O is the center of disk S, right? And they're in line with one another, right? They're in line with one another. So I'm just going to draw these on opposite sides like this. This line, right? So point P is somewhere, let's say here. Here's P, right? There's P. And so we end up with this triangle here, right? And we're going to say that there exists some other point, P prime, that is the point on disk S, right? So this is where P touches disk S, right? And they're coincident, right? That's like we had on the collar, right? Point P and point A were the same in space, but it's just, are we measuring this from O or are we measuring this from B, right? This is the question, right? That's what we're doing. So we can figure out there's some angle here. We know this angle is phi, right? So this was our 150 degrees right there. There's some distance from here up to here that we're going to call R. This distance here, so here, right, was capital R, which we were given, 0.05 meters. So we can figure out, right, because then this angle in here should be 30 degrees, yeah? So we should be able to use law of cosines to figure out this green R. All right, so by the law of cosines, what do we get? The law of cosines tells us that R squared is equal to R, capital R squared plus L squared. What's L? L is the distance here between the two disks. Minus 2 times R, L, cosine of 30 degrees. That's that 30 degrees right there. Okay. We can plug in all these things. Right, we know all these things. What was L? Good question. L is equal to the square root of 2 times R. How did we know that? Magic? No, we were told. It's literally given to us. I made it up, guys. Yeah, I didn't do it. Imagine, right? So we plug it, we chug it, we get that this is 37.1 millimeters. Okay. But we want to know this angle beta, right? So how do we find beta? We're going to use law of sines. Sine of beta over 0.05 is equal to sine of 30 over 0.0371. We can solve that, and beta is 42.4 degrees. Okay, so that's the geometry of the situation at 150 degrees. All right, so that's the geometry. How is that going to help us? Well, remember, we're going to need components, right? We're going to need components in x and y directions, and that's where the angles come into play. So let's, all right, so is everybody okay with this so far? We okay? We doing okay? Yeah, maybe? Maybe not? We're going to keep chugging. So that point P, right, is attached, is rigidly attached to disk D, right? It's rigidly attached to my turntable. And that turntable revolves around point B. So I can find the velocity of point P, the absolute velocity of point P, which has to be R times omega D, right? There's some point, remember, the turntable looks like this. I've got some point here, right? This is point B. I want to know, I know omega, right? I want to know V sub P at this point in time. It's omega cross R, right? That's what it is. So that's what we're going to have to do. We're going to call that omega D, right? R times omega D, which gives me 50 millimeters times 10, which is 500 millimeters, if I can get that, millimeters per second. And so we're moving with a velocity of 500 millimeters per second, and that is pointed which direction? Tangential to the path at that point, which is directed downward in the slot, right? So if we remember, right, this, here's the top half of my Geneva mechanism, right? Something like that. And you've got this pin in here, right? That's on my other turntable here, yeah? This velocity is going to be pointed down that slot, right? At this point. It's going to be tangential to my path here. Okay. So I know VP. What is that angle, right? Let's talk about that. So if this is tangential to my path, right? What's this angle in here-ish? 30, 32. We can figure out that angle, but is that really the angle that we need? Right? What we really want is this one, right? What we really want is that. It turns out that this angle here, right in there, is going to be roughly 60 degrees between the two. This is down at 60 degrees. the equation that we are trying to solve, right, is this. Now, this is a little bit different than what we've been talking about before. Why is it different? Because we already have VP. Remember, what are we trying to find? We're trying to find the angular acceleration of disk S. We're trying to find the angular velocity of disk S, and we're trying to find this term right here, right? Those are the three things that we're trying to find. We already know what VP is, so I can look at just these things in their parts, right? So what is VP prime? Well, we can come up with an equation for VP prime. So let's look at this, right? Here's point P. Here's point P. We know that this has some velocity. That's VP. VP prime will be here. And VP with respect to S is here. From this, I can say, well, I know this angle has to be beta in here. I'm going to call this angle in between these gamma. And this angle here is 30 degrees. This is 90 over here, and this one is 60. It's where the 60 comes. Gamma has to equal 90 minus 30 minus 42.4. So this is 17.6 degrees. Let me write this over here. VP prime, right? Because this is a right triangle with VP as the, I didn't draw it very well, but this is a right triangle in here. VP prime is just VP times the sine of gamma, which is 500 sine gamma, which is 17.6 that we just found. So VP prime is equal to 151.2 millimeters per second. And that's at an angle of 42.4 degrees, right? It's going to be down at beta. VP with respect to S then has to be VP cosine of gamma, which is 500 cosine 17.6, which is 477 millimeters per second at 42.4 degrees. I draw the other one. All right, so what did we do? All right, I know what the absolute velocity is. Remember, the absolute velocity is the total of the velocity as seen from the moving frame and the velocity of my point with respect to the rotating frame, right? Okay, so if I have that, what can I do? I can draw this triangle, right? And I know that if I have the total velocity, then the other two have to be components of that velocity. And they're going to be at 90 degrees to one another, right? And that's all I've done here is I've broken down V sub P into its components, right? This is different than how we've been doing some of these problems and how we've been talking about this, because normally we're looking for V sub P, right? Normally we don't just automatically solve for it. So we got VP with respect to S. We got VP with respect to S. But we know something else, okay? We know another thing here that's going to help us. We know, and I'm going to draw my Geneva mechanism again here. Right, something like this. I know that this point here, P prime, I know that this velocity is perpendicular to the slot, right? perpendicular to the slot. So if point O is someplace over here, right? And that's what's driving my motion, right? That's some distance r away. Then VP prime is just equal to omega s times r. So omega s is equal to VP prime divided by r. We know VP prime, right? That was 151.2. We know r, that's 37.1. And so omega s is 4.08 radians per second. That's omega s. And the last part of this has to deal with us figuring out the acceleration. AP is equal to AP prime plus AP with respect to my rotating frame plus my Coriolis, right? Plus my Coriolis. This is the acceleration equation that we've been using. In this case, I know omega d is constant, right? I was told omega d is constant. We wrote this down earlier. That means that alpha is 0, right? So that means that I would only have a normal component of the acceleration due to p, right? So AP, the magnitude of AP is just r omega s squared. Sorry, of AP. Yeah, I did that the wrong way. Sorry. I was looking someplace else. I apologize. Omega d squared, capital R. This is 500 times 10, which is 5,000 millimeters per second squared. Okay. We can talk about AP prime. This is going to have a normal component, which is r times omega s squared, which is 37.1 times 4.08 squared, which is 618 millimeters per second. There's also going to be a tangential component. The tangential component is what we need. We're going to end up picking up our alpha term that we need to solve for, right? Alpha s. My Coriolis term, the magnitude of my Coriolis is 2 times omega s times vp with respect to s, all of which I already have. So I'm going to plug those in. 2 times 4.08 times 477 gets me 3,890 millimeters per second squared. And now I've got everything, right? I've got expressions for all of these, right? And I can plug them in and I can get a big old equation where I can solve for alpha. So what do I get? Well, I'll get A sub P is 5,000. That's 30 degrees downward. This is equal to 618, which is 42.4 degrees down to the left, plus 37.1 alpha of S, which is 42.4 degrees down and to the right, plus the acceleration of P with respect to S, which is up 42.4 degrees to the right, and 3890 up and to the left, 42.4 degrees. So we're going to break things into components that are perpendicular to the slot. And if we do that, we get 5,000 cosine of 17.6 degrees is equal to 37.1 alpha S minus 3890. So alpha S is equal to 233 radians per second. This is a tricky problem. Are all of the rotating frame problems tricky like this? No. We're going to do another one next class because we obviously don't have time to do it today, where we contract the rotating frame of the wrist based on the shoulder and elbow, right? So basically, we're going to look at somebody shooting a jump shot and how do we track the motion of the wrist from the elbow and how do we track it from the shoulder. That's a little bit more of a real world problem, right? Especially if you get into robotics. Robotics is all about reconciling all sorts of different reference frames that are working. Yeah. Let's see. Yeah. You guys have any questions about this? We're going to cut this one right here. We'll get into general motion next class. We'll do a brief review of cross products and oh, don't forget, guys, don't forget, please don't forget that your participation this week hinges on you coming to class on Friday dressed for Halloween. There's also a very mandatory fun, and it's mandatory fun, right? So you know it's going to be good because you have to have it. We're going to have a mandatory fun participation activity at the end of class on Friday. It's a Kahoot. All right. That's all I got. I know it's a lot. You know, if you have any questions, I've got office hours after class from 3 to 5. Then again on Friday from 3 to 5. Right? Guys have a homework due on Sunday. Oh, you'll see. No spoilers. No spoilers. Unless you see me tomorrow, because I will be dressed in the same costume tomorrow. Yeah, exactly. So,
Go back to this.
yeah. Give me one sec. Which part of it? The
Yes.
okay, why don't I put it up here? So you let me know. The very end, you said the components. Like this one here? Take it easy, Logan.